Okay, so what I would like to do is I would like you to draw these two diagrams. This is the electron configuration. You did this in Gen Chem or in Basic Chem. We only need this portion. We're not going to re-explain it because we don't have the time. But if you recall, carbon was 1s2, 2s2, 2p2. Those are the orbitals and the energy levels. And next to it is here's the orbital diagram according to their energies. So if you recall, you had to do the half-headed arrows for the electron's spin. So the 1s has 2 electrons, so that would be up, down. The 2s had 2 electrons, so that would be up, down. And then the 2p would have 2 electrons, that would be up, up, because you had to put them parallel with parallel spins and then go back and pair when you have enough. Nevertheless, what we need to care about is the 2s, 2p portion. Now, a bond forms when you have that number of unpaired electrons. In this case, we only have 2 unpaired electrons. So this is a dilemma that chemists faced almost 100 years ago. How can you have 2 unpaired electrons, yet we have a very important example of methane, where carbon has 4 hydrogens attached to it, which means carbon has 4 unpaired electrons. How can that happen? Well, the only way they were able to explain this is by using the theory of hybridization. Hybridization simply is a way of explaining how the bonding now goes from 2 unpaired to 4 unpaired electrons. So, atoms, atomic orbitals on an atom mix to form what we call new orbitals called hybrid orbitals. And the hybrid orbitals have different shapes. And I know I wrote over this, but the number stays the same. So if you start with, let's say, 3 orbitals, then you end up with new orbitals, and their number would be 3. So let's look quickly, go to the most common type of bonding. So the way to do it is to take your 3p orbitals and mix them with the s orbital. So if you recall the shapes of the p orbitals, they look like an 8 or an infinity sign in 3 different axes. And then you have the s orbital, which looks like a sphere. If you mix them all together, combine them, you will get 3 new orbitals. So this process is called hybridization, or we just say hybridize. And they kind of look similar to both, or has a combination, hence the word hybridization. So they have now a larger lobe and a smaller lobe. Okay, what's so fancy about this? All you have to remember is this is a region where the electrons are in, or most likely to be found. So actually this brings us, if you put all of these together, if you notice, we have 4 atomic orbitals. And we end up with 4 hybrid orbitals. If you put all of these together, you will see that the larger lobe is the one where the bonding is going to take place. The smaller lobe are shown only in this case, but they won't be shown from now on. So here's methane for you. The geometry actually comes from hybridization. So in this case, you have carbon, and that each has an unpaired electron. So what happened on this diagram? Here's the 2s. And here's the 2p. We took them from right there. What we do first is, in order for us to have 4 unpaired electrons, and think about them, is we have to unpair these 2. So we take one of them and put them in there, put that electron in its own orbital and the p orbital. And then we hybridize. We mix them all together. When we mix them all together, we get 4 unpaired electrons, and we call them sp3. S and 3p orbitals. That's why it's called sp3. Now, this is what the big deal is. Now you have 4 unpaired electrons, which explains why carbon has 4 unpaired electrons. So hybridization is important because it takes into account quantum mechanics. And quantum mechanics is the theory that we use in bonding, in chemistry, and in physics. So that explains it. Now, what happens if you have less hybridization occurring? If you notice here, you have only 3 atomic orbitals. So you have 2 p's and 2 p orbitals and an s orbital. Well, what happens is you do end up with 3 hybrid orbitals. But one of them, this one, remains unhybridized. And we're going to need this for the next topic of pi and sigma bonds. So then, okay, here are your hybrid orbitals, 3 of them. And these have a name. They're called sp2. So what happens here? Similar. Say similar, not the same. So in order for you to have now 3 unpaired electrons, you actually promote one of them from the 2s to the 2p. And when you hybridize, you only notice what's happening here is you mix 2 p orbitals and an s orbital. So you mix actually these and you leave this one unhybridized. And that's how we can explain the sp2. So here it is, 1, 2, 3, and there you go for the 2p, which explains the hybridization on ethene or ethylene. So finally, for sp, you have, so let me jump right away here. You still do the promote, you promote that, and I'll explain why. And when you're mixing in this case, you're mixing a p orbital and an s orbital. So you have 2 atomic orbitals. And you end up with 2 hybrid orbitals. But you have 2 unhybridized p orbitals. So here you go, 1, 2, and then you have 3, 4. Now notice the key here. These add a higher energy, the p orbitals, than the sp. The whole point of only mixing, and let me show you the mix. Okay, so by the way, we need to actually delete this one, the one we promoted. The whole point of mixing them is to actually lower the energy. And it's, if you notice, it's somewhere between the 2p and the 2s. You see that? And that's why also hybridization occurs to create or to make 2 unpaired electrons. And that gives you right here 180-degree angle because you have 2 electron groups. Say, you know, the the two unpaired electrons. Now, all of this is, I understand, is theoretical, highly theoretical, abstract stuff, but it's important in explaining the bonding to us. So the when we meet on the next time, when we meet on Thursday or whatever the day is, Thursday, we will go over this more in depth. But for now, it's giving you some prior knowledge in understanding it.